Anoop is currently a postdoctoral researcher at Cooperative Agriculture Research Center, and he joined uh, mid of March 2021. He earned his PhD in water resources engineering from Clemson University, and he did MTech in water management and BTech in agricultural engineering. He has worked as a postdoctoral researcher at USDA-ARS, Fort Collins, and Colorado State University before joining PVMU. His research encompasses the application of physically based hydrological models for addressing real-world water quality and quantity challenges. His research also focuses on the impact of land use, climate change, drought, and water scarcity on regional water security. With uh, Dr. Arnold, he's presenting today. His title is Towards Sustainable Agriculture and Water Security. Let's welcome Dr. Arnold. I'll stop my screen and you can see our screen. Okay. 20 seconds.
It's okay, right?
Yes.
Okay. Thank you, Dr. Ravel, and good morning all, and thanks for participating here or attending my seminar. I'm Anoop. I'm currently a postdoctoral researcher at CARC, and here I'm trying to present some of my research I did during my PhD and after PhD. And the topic is towards sustainable agriculture and water security. Yeah, as Dr. Ravel mentioned, I did my PhD from Clemson University. It's that's also a land grant university in South Carolina. There I was focusing on the research related to water security, drought, water quality, drought resilience, yeah, those topics. And after that, I moved to USDA Fort Collins. That was a combined project with USDA and Colorado State University. And there I was working on a new model called agriculture ecosystem service modeling for simulating stream flow and nutrients. And after that, actually, it took me around 6 months. I moved from USDA to Prairie View, the agriculture center. And here I'm working with Dr. Ali Faris and Dr. Ravel. And here we are focusing on some sustainable agriculture, water, food, energy nexus, then irrigation, water quality, and other field experiments. The first topic, I will try to present some of my work. I did it from Fort Collins. And the heading is the modeling flow and the nutrients in an agricultural perspective. So as a background, we can see here, because of eutrophication caused by human activities that happened or that's currently going on, it will take at least 1,000 years to recover completely. It it's it's uh, it's from EPA, and for eradicating this nitrogen and phosphorus, uh, drinking water facilities and individual individual Americans are spending almost
You can continue. On. On. You are muted. On. You're
Is it okay now? I
oh
have
yes.
no idea how that happened.
Oh,
Okay. Then, yeah, in this presentation, majority of the section, I will be focusing on hydrological modeling or watershed modeling. So in this figure, you can see a water cycle, or we call it as hydrological cycle. So we know a watershed, briefly, a watershed means it's the area of land which drains water into a particular stream. So in a watershed, yeah, as you know, we have, if you consider one watershed, we have agricultural lands, urban land, some other industries, forest land, everything. So, so a lot of activities will be going on there. For example, uh, we will be growing crops, and as a management practice, we will be applying fertilizers, pesticides into that field. So that uh, those fertilizers and pesticides finally that will reach to the stream. So what uh, in modeling, what we are trying to do is we try to represent that water cycle or this watershed in a computer. So for representing that watershed in a computer, we use different inputs like topography. We call it as DEM or digital elevation model. So first thing in modeling is we download and process that topography data. Then we will try to understand the land cover of that area. So USDA is providing land cover maps. Then after that we will go for soil map, which or what type of soil is filled in that watershed. Then based on this information, we try to delineate the watershed. That means if the outlet is located here, then we will try to calculate how much area is contributing water to this particular outlet. So yeah, this figure, it looks like it's an example for delineated watershed. So once the watershed is delineated, we will try to include or add data like precipitation, temperature, relative humidity, solar radiation, and wind speed, etc. So if we are focusing on stream flow simulation, we will stop here. We'll add up to wind speed. And further, if we are focusing on nutrient simulation or water quality simulation, we will try to add other inputs such as fertilizer amount, pesticides we are using for the crops, and if we have some wastewater treatment plants, we'll try to incorporate data from those facilities. Then once the model is ready, or I can say most of the hydrological models, the basic equation or the basic thing is water balance. So water balance means we will try to equate the soil water, incorporating the precipitation, surface runoff, evapotranspiration, percolation, and groundwater flow. So once the model is ready, we will try to calibrate the model with observed stream flow data or observed nutrient data from the stream. And USGS is providing those information, basically the stream flow information, and EPA is providing the water quality information in a stream. So what I mean here by model calibration is if we have 10 years of data, 10 years of flow data, we try to equate, or we will check the model simulated stream flow, and after that we will check the observed stream flow. And for calibration, we may consume or we may use 7 years of data. Then after that, 3 years of data, we use it for validation or testing the model performance. I think it's clear, and I can go to the next slide. So with these informations, uh, in USDA, we tried to model one agricultural field. So as I said, uh, there are numerous watershed models or hydrological models are available in the field for a particular task. That's always a question. So when I joined there, the USDA Fort Collins, they have a in-house watershed model. It's called AGES, Agricultural Ecosystem Services Model. And there is a famous model called SWAT, Soil and Water Assessment Tool. So that's a well-known model, and we were confused which model we should use for simulating the watershed or simulating the agricultural area there. So initially we did a comparison study between AGES and SWAT. And another concern is uh, I I explained about the model calibration. So if we are considering a watershed of 500 kilometers square or 30 kilometers square, we may have only uh, what inflow or outflow data only for, or the stream flow data only for one or two locations. So always what we try to do is we try to calibrate our model for that particular two locations. So and of course we will get good results, maybe in this Nash circle efficiency or some goodness of statistics around one. But the spatial accuracy of the model within the watershed or interior watersheds, it may be less, and it depends on the models. So we try to select a model that means ages or SWAT for that particular study. So as I said, ages is a new model, and these are the input data we need for developing this ages model. So we need the digital elevation model that says the topography of the land. Then we need soil data, this field boundary. Then this model has a hydrogeology section. That means this model is good for representing some part of groundwater. Then once we have all this information, we can use some delineation tool. It's called catchment area delineation tool. That's also developed by USDA and CSU. Then based on delineation, we get uh, sub catchments, hydrological response unit that says within the sub catchment how much of forest we have, how much of agriculture we have, those information. Then we get the stream network. Then once we have this delineated area, we can use that as an input to LAMPS, because we have to use LAMPS because LAMPS, it it says what is the crop rotation practice for that particular area. So once we have the delineated watershed, we can get in each field what was the crop rotation practice the farmers are following for last 10 years or 15 years, how much in it. Then another major input is discharge from wastewater treatment plants. So we had three wastewater treatment plants in that watershed, that in the study area. I will explain that. And another inputs are weather inputs, that's precipitation, temperature, etc. And we put all this information to a model. It's called, the model was AGES. A model means it's a combination of equations. It's nothing, it's combination of equations. And uh, we try to calibrate the model uh, using the observed stream flow or observed nutrient concentration. Then we get the output. Then the next slide, it explains the steady area. So our steady area was, or it's located above Denver and below Fort Collins, where the university is located. The total area of the watershed was more than 200 kilometers square. And as you see here, we have all the agricultural lands which are located in this southern part here. So the major agricultural products are corn, alfalfa, then grass, then winter wheat. So we were trying to model only this area. You can see the watershed is split into two, and we got a USGS inflow station for this location. So we use that an input to the watershed, and we had a outlet located here for calibration. And yeah, these are the wastewater treatment plants located in the watershed. As you see here, we had 3 wastewater treatment plants, and you can see the contribution of water from the wastewater treatment plants. It differs from month to month. It's because of the wastewater treatment plant. The green is Westminster. They are storing the water for reuse uh, from June to September. So you can see less flow here. After that, they are releasing the water to the stream. So you can see high flow here. And for uh, it's the red is Broomfield wastewater treatment plant. They store the water during November, December, and January and February. So what I want to say is it's this data is important for modeling purpose or for accurate result because it has a lot of influence in the stream flow on the stream flow, especially for the base flow. And uh, we provided all those input to the model and we run the model. And after that, we calibrated the model and it shows the calibration result. So we calibrated the model for 7 years from 2012 to 2018. Then we tested the model for 2 years. That's for 2010 and 2011. And here you can see I have used 2 models, that is AGES and SWAT. The goodness of its statistics is better for AGES model. You can see NSC, it's 0.777, it's very high. And the KGE, it's comparatively new metrics. It's called Kling-Gupta efficiency, and it's good for catching low flow. So you can see 0.88. So that means when if the value is near to 1, the model is good for predicting the results or predicting the stream flow. Then these are the input. Uh, yeah, it's AGES and SWAT. Both are different models, so we have to, and both the models use different interpolation techniques for precipitation. And we have when you give the location data for precipitation, maybe AGES may not take that particular location for as an input. Maybe SWAT may not take it as an input because of different interpolation techniques used within the model. So we try to equate the precipitation and irrigation in the model as same, but still you can see some difference, a small difference. So based on that, the model predicted evapotranspiration and water yield in different amounts. Here you can see for AGES, the evapotranspiration is high, but here the evapotranspiration less. And the major difference is observed in water yield. So basically the water yield is the sum of groundwater flow, lateral flow, and surface flow. So the major thing we noticed is for SWAT, the lateral flow was almost zero. It was like annual lateral flow we got around 1 millimeter something. So that means there is something wrong going with that SWAT model, especially for that location. And I think this figure explains what is the major difference between these 2 models. So for SWAT model, you can see the flow only in the output location. And for AGES, that's in the green color, you can see or you can understand what is happening inside each sub-watershed. These black sections are called subcatchment or sub-watershed. So that's basically, we can say this is the difference between a semi-distributed model and a fully distributed model. And this figure, it's a good comparison between or the flow comparison between ages and SWAT. So here you can see in the upper watershed area, that was the major uh, urban area was located here in the upper watershed area. So here we have high uh, surface flow. SCRQ means surface flow. But when you go to the lower or the agricultural land, the surface flow is almost zero. That should be true because that's a semi-arid area and almost all the water should be evapotranspiration or evapotranspired. And but when you look at the SWAT model, we can see we have less water in the upper watershed, but high water amount in the SWAT model. That means in SWAT model we were using a methodology called curve number method for simulating the surface flow and infiltration. So when you add water, the SWAT is transferring that water as surface flow, and the remaining water is going to the groundwater flow. It's not accounting much of the flow to the lateral section or the I mean lateral flow means the flow through the soil section. So this was the difference we noticed between ages and SWAT in flow. And this figure shows the comparison between ages and SWAT from return flow from the irrigated field. So SWAT was predicting a high return flow from the irrigation field, and the ages was predicting a low flow. But there are some outliers for very big values for ages flow. And finally, we tried to calibrate the model for uh, nutrients, that's nitrate. And here also we can see, actually we were lucky to get these 6 locations uh, from Big Dry Creek watershed associations, which are located within our study area. So here you can see ages was comparatively better than SWAT model for predicting the nutrient or the nitrate for these 6 locations. Then I can our major findings were ages simulated the stream flow better than SWAT, stream flow and the nitrate concentration. Then, yeah, both the model simulated the water routing in different amount or in a drastic that was, yeah, entirely different. And after that, our second objective was use this ages model for conservation practice, or we tried to implement conservation practices within the model. So we are trying to implement the conservation practice, for example, flood irrigation. What will happen? Actually, the most of the watershed is irrigated using flood irrigation. So what will happen if we change that flood irrigation to sprinkler irrigation? And what will happen if we follow tillage or residue manage within the field? And uh, what will happen if we adopt different fertilizer application techniques in the field? So it's an ongoing study. So I did not include any results for this study, this particular study. And yeah, I will try to explain some of my work from PhD. So in PhD, I was focusing on water security and drought. Most of them was related to water quantity. So as a background, so, we have there is a paper published in 2016 in Science Advance. So based on their results, 2/3 of the global population, that means more than 4 billion people, live under severe water scarcity situation, at least for 1 month of a year. It's a paper published by Arjen Hoekstra. He was a scientist from Netherlands, and he started the concept of this water footprint. And yeah, as you see in the figure, you can see US is spending more than $435 million for eradicating this water security or water scarcity. And a background to the drought. The figure you can see here, it's a drought, the global drought from 2016. And drought is considered as one the deadliest disaster. And for the last 5 years, the total number of fatality was more than 3,500, and US is spending more than $9 billion per year for recovering this drought related issues. And what you mean by water security? So when we say a area or a region is water secure, so that the water resources in that area should be able to provide water for human well-being and at the same time for the ecosystem functioning. So as you know, uh, when we see a water resource, we cannot abstract or we cannot withdraw 100% water from that resource, for example, by a stream. And according to SDG 6 uh, by UN, it's uh, for human purpose, we can only withdraw 20% of water, and we have to leave the 80 percentage for ecosystem functioning. And yeah, as you know, water security, it's very important because it's related to our day-to-day activities. And I will try to introduce some uh, concept in water security. It's called blue water, green water, and gray water. So when you say blue water, it's the amount of water stored in surface structures, for example, reservoirs, uh, and in the groundwater systems. That means in the aquifer. And we have green water. That means the direct amount of uh, precipitation which is stored in soil layers. So plants can directly use it. So that is important in the field of in rainfed agricultural field. Or then gray water, it's the amount of fresh water required to assimilate the concentration of nutrients. So yeah, we are discharging this fertilizers or waste effluent from wastewater treatment facilities to the streams. So we have to make sure that, uh, or it's like a notion or a theoretical concept. It's like if we are adding this much of nutrients to the stream, so how much water we need to add to assimilate or make that concentration to the natural level. And based on this blue, green, and gray water concept, we have the water footprint. Here, the blue water footprint means uh, the amount of water consumed from the blue water, and the green water footprint means it's the amount of water consumed from green water. Actually, this gray water and gray water footprint, it's the same, but people say it's like gray water. In some publications or some studies, they use gray water footprint. It's the same. And we try to apply this concept of water footprint in a watershed located uh, in eastern USA. Actually, it's a transboundary watershed shared between Georgia, South Carolina, and some portion in North Carolina. So the total area of the watershed was around 30,000 kilometers square, and we had around 31 counties located within that watershed. And the major thing here is we had 3 reservoirs within the watershed, with which is with divert water for irrigation and some other household use. Then yeah, we try to apply this water security concept here, and this is the modeling framework we applied. So we were using the SWAT model for this task, and once the model is calibrated, we try to extract the amount of water we have in each sub catchments or each counties, and we try to calculate the water scarcity. Basically, that means water scarcity means uh, amount of water, the amount of water used to divided by the amount of water we have in that watershed or in that county. And these are some results. So the green water scarcity, that means the ratio of uh, the water used by crops to the amount of water we got from precipitation. It was like in the southern part of the watershed, the water scarcity was high because most of the soil in this section was highly sandy, so it drains water too fast. So the amount of soil water will be less here. So the water scarcity was high in that area. Then we try to calculate the blue water scarcity. So when I say human water, it represents the water used for municipal water, domestic purpose, industrial purpose, and hydroelectric power generation. So basically we try to calculate water scarcity for human use and agricultural use. Agricultural use means uh, it's the water used for irrigation, for livestock, and for aquaculture, etc. So it shows the competition between human water use and for irrigation use or for the agricultural use. And we try to extend that study for understanding the impact of land use and climate variability on water security. So for Savannah River Basin, we can see the developed area was more than uh, 247 percentage from 1992 to 2011. So based on this information, we tried to calculate the water scarcity. I mean the effect of land use and climate variability on water scarcity. And as you see here, the blue water scarcity that's in red color. Red color indicates high blue water scarcity increase for these two counties, and the high green water scarcity was in these red counties located here. Then after that, we tried to calculate or quantify the water security of entire United States. So here the graph which shows the water usage uh, for human water and for agricultural sector for last 25 years average. And this we have 18, we have considered 18 major river basins located across the USA. I can show the images of that in the next slide. Then we used the model output data from Vic model. It's the model output data is directly available from uh, a website maintained by NASA. It's called I forgot the website. I think it's called NLDAS. That means National Land Cover Database something. And we directly use the output from Vic model provided by that website. Actually, Vic model is used for calculating surface flow and lateral flow. We don't have any information for ground flow, so we were using the surface flow information for calculating water security. So these are the major 18 river basins I was discussing. Uh, so as as you can see here, the blue BW means the blue water. That means the surface water availability for USA. So in western sides, the amount of available water is comparatively less to the eastern side, and the right hand side figure shows the uh, green water footprint. So it's green water footprint. We can only analyze it for uh, rainfed agricultural lands because green water is directly linked with the rainfed agricultural land. Then here it shows the amount of green water storage. And I will go to the next slide. It explains the spatial distribution of water scarcity. So GW scarcity means the green water scarcity for rainfed agricultural land. So we can see for uh, the Florida area, the green water scarcity is high. And when you come to the blue water scarcity for human use, we have high blue water scarcity for the states located or the watersheds located in the western area, and the blue water scarcity for agriculture it's very high compared to human use, and that also it's very much higher in western side. And we try to analyze an index called Falcon Mark index. It's basically uh, the amount of water used by population. So yeah, we calculated the unit is meter cube per capita per year. So that represents how much water the population is used for a particular region. Then we have 20 more minutes. I'll try to explain one more work. I did it from Clemson. So drought, yeah, as I explained, drought is a major concern now. So we tried to predict the stream flow drought. It's called hydrological drought for Savannah River Basin. So uh, we were we we were using different variables. For example, average precipitation over the Savannah River Basin, base flow index, stream order for predicting the drought across that. I mean, these are the different variables we selected for predicting the drought. And based on our drought prediction using different climate and catchment variables, we got this result. Actually, it is called a decision tree. So we can see uh, if the pasture land is less than or higher than 12 percentage and the stream water is more than 1, the number of or the drought duration will vary between maybe 28 months to 45 months. So this is how we can explain this figure. And yeah, after that I will try to explain one work I we did it from here in Prairie View. So we had a winter storm in February. It started from February 12th to February, and the effect was there, or the snow was there until February 21st. And this figure, it shows uh, the spatial pattern of temperature. So we can see in February 13, the temperature went up to negative, I think negative 13 something. Then that started increasing, or for I mean, this number shows the climate divisions. We have 10 climate divisions across Texas, and for climate division 6, the temperature started increasing from February 16. So it went more than 0 degrees Celsius. So we tried to understand, or we tried to study the impact of this winter storm Uri on drought and uh, soil moisture and vegetation. So for example, uh, here you can see drought for the month of January 2021. So we can see for the Western climate divisions, the drought was high, but in February, that is during the month of Uri, for some of the small sections are uh, counties. For some of the counties, the drought became normal, or the severity decreased, and it became like January in March. So we can conclude that there was some impact of Uri that helped the western area to minimize the drought severity. And here you can see the graph here. It's varying from -4 means high severity, and yeah, +4 means there is no drought. And yeah, here I try to find the relationship between soil moisture and snow water equivalent. So the soil moisture is in cubic meter, and you can see some kind of relationship between SW means snow water equivalent, So the snow water equivalent, we know we don't have uh, much data of snow water equivalent for Texas, but there is a website called Climate Grid. They have some remote sensing data or model data for Texas, especially for during that Uri event. And we can see some kind of relationship between uh, this soil water equivalent and soil moisture. A small r, I mean, the correlation coefficient that was uh, for February 21st, it was showing 0.44, and it showed a high correlation during March 1st. Then it started decreasing, and I have noticed up to April 30th, it showed a value more than zero point 0.4. That shows there is a kind of relationship. There is some relationship between these snow water equivalent and soil moisture, and that helped us to decrease the drought during February. And finally, I tried to understand uh, how the Uri, the winter storm, affected the vegetation. So for that purpose, I was using a remote sensing based index called normalized difference vegetation index. So it's the equation you can see here. If the NDVI value is less than, or if it is -1, we can say there is no vegetation, and if the value is close to 1, we can say the vegetation is healthy for that area. And it is calculated based on the reflectance curve, which uses the wavelength and the percentage of reflectance. And yeah, these are the results for changing vegetation. That means NDVI. And for the first week of February, yeah, the vegetation was looking like this. Then we had the winter storm effect, so that washed almost all the vegetations in the eastern Texas. Then from the third week onwards, we can see there is a growth, or it recovered. There is resilience, recovered the vegetation. And here you can see the percentage change or percentage decrease. That means from first week and fourth week, it shows for CD10. That means here we had most of the vegetations were influenced here. That was like more than 8% of vegetation were washed, and that is not came back within this 1 month. And with that, I will conclude here and thank you for this opportunity, and thanks for listening. That's it.
Okay. Thank you, Dr. Anoop.
Thank you.
Uh, uh, is there any question for Dr. Anoop?
Dr. Veettil, this is Gerard D'Souza. If you can see me, I'm just migrating to a new computer and multitasking on two Zoom calls at the same time. Can you hear me
Yes,
okay?
I can hear you. Yes.
Okay, okay. So thanks so much. Very, very interesting discussion.
Thank you.
And you've got a fantastic background. I can see now why Dr. Fares and Dr. Hawal and so on were trying so hard to get you to come here to Prairie View. Your background is ideal for this area, as we witnessed from recent water-based events. And I was multitasking. I had another conference call from the registrar's office, university update. But I did get from your talk the importance of water security.
Yes.
And we are already here at Prairie View College of Ag known for food security, now becoming known for nutritional security. And of course, water security is also a very important concept and needs to be front and center, because there's thousands of homes in the Southwest Houston area still without power as a result of the recent water damage, wind damage, and so on. So it's hard to be food secure and nutritionally secure when your house is flooded or doesn't have power. So I think your talk on water security is very important, and certainly resonates with me and our stakeholders in the Houston area. So thanks so much for a very great talk, and look forward to hearing more over time.
Thank you. Thank you.
Uh, is there any other additional questions? Uh, I have one question, Anoop. Uh,
Okay.
like you just tested that AGES model and SWAT in one water site,
Yes.
and based on that one, like that model is better than SWAT is.
Yes.
Like, did you check in other water states, or do you have plan to check in other water states, like so that we can generalize like that model is better than SWAT for those stream flow and nutrient modeling? Okay.
Yeah, actually, I mean, it's a lot of work. I mean, basically, it takes long time for a perfect evaluation for two models. And what I have noticed is we currently the SWAT, they developed a new model called SWAT Plus. It's a fully distributed model. So they are saying much of the drawbacks from the SWAT model they try to address in the SWAT Plus. So I think instead of checking with the SWAT model, if we can compare this SWAT Plus and ages model, that will be a good study.
I
Yeah.
think next part maybe better to check that SWOT plus.
Yeah, they were the USDA, the group, they were discussing that. Yeah, but yeah, I mean, by the time I left USDA, I mean, the SWAT, I think the SWAT Plus, they recently released it, but I was not there. Yeah, but they are also interested in on that study.
We have still 9 minutes more. Is there any question? Like in this presentation, he summarized uh, his PhD work and his postdoc work, at least 3, 4 papers, uh, and 2 unpublished work. So he covered many things. It's a little difficult to understand
Yes.
all, but I think in general, is there any question? Dr. Ellison? Yes, please.
No questions so far, but I'm wondering for the model you've mentioned, it's a fully distributed.
Yes.
How you describe this distribution? Is it
So
based on HRU
yeah,
or
exactly.
on grid?
It's basically, yeah, that's
How you
a
distribute the input? Sorry, how you distribute the input parameters?
yeah, that's a great
Physical
question.
parameters. Is
Okay,
it
yeah.
based on a grid or HRU?
It's based on the HRU. Yeah, thank you for asking that question.
Yeah,
So,
thank you.
so basically, I think when we say a fully distributed model and SWAT model, SWAT is a semi-distributed model. So when we say a fully distributed model, that that is spatially explicit. That means it shows flow from one field to another field within a watershed. So we can measure or we can quantify that flow in a fully distributed model. But when you say it's semi-distributed, it calculates the flow from each field or from each HRU or from each grid, and it lumps everything and it gives the uh, output as a mean or as total or sum.
Yeah, but does it
So
does it simulate I mean,
It simulates. It simulates,
represent,
but
yeah,
yeah, it
parameters.
simulates the flow or the amount of water, but it will not show the routing. That's the major difference.
Okay,
And
one
yeah,
more.
exactly. It's the one HRU here is one field.
In SWAT.
One more question. I see this model is as you said, as you mentioned, for agriculture application and practices is better than the older version of SWAT.
Yes.
But I'm also wondering about the output time step data. What is the minimum one? Is it daily based? Can
It's
it be
daily based. It's daily
in
based.
minutes?
It's 15. They are developing the 15 minutes
Mhm.
one, but still that is not available. But if you, I mean, if someone is interested, they can contact them. They will give the model.
Okay.
Yes.
Thank you.
Trying to repeat. Yeah, thanks for that question. That's it.
Is there any additional question? No question. Okay. Okay, can I see your that screen? Can you stop that one? You can see my screen, yes? No?
Yes.
If you if no questions for the Anoop, I just want to remind you all, like we have still some days remaining slots, like September 30th, then 21st October, 4th November, 11th November, and 2nd, 9th, and 16th December. If you are interested in presenting in this research seminar, please let us know. Like we are still looking for more presenters. Next week, we have speaker from Texas A&M University, Dr. Ravi Maharton. We will use the same Zoom link at the same time next week on Zoom. Dr. Anoop, do you want to say something at the end?
No, that's it. I mean, yeah, thanks for this opportunity. I think if all the postdocs can give a presentation on this slot, that will be good. That will be a good experience.
Okay, if no questions, we will stop here. Thank you all for joining today's this seminar. I'll see you next week at the same time with new guest speaker. Thank you all.
Thank you.
Bye.
Thank you. Bye-bye.
Thank you, sir.
Recording stopped.